Hello, everyone, and welcome to this special, distinguished S3D seminar, joined also with the Privacy Engineering Seminar. And today we've got, we're lucky enough to have Professor Kassem Fawaz visiting from Wisconsin-Madison. Professor Kassem Fawaz, or Kassem, is an associate professor in electrical and computer engineering at Madison, Wisconsin, and he is also associate chair. He's actually a chair professor, I believe. I don't remember the name of that chair, but you're going to forgive me for that. He's also associate chair for research, which is a new thing, I believe, in his department, and so he's figuring out what that means.
No, we know. This is recorded, right?
Okay,
yeah, we know everything.
We know exactly, okay, what it means. And he's well known for his work in security and privacy. Got his PhD at the University of Michigan. He and I have been interacting for probably close to 10 years at this point. And he's a pretty amazing guy. He's received a number of awards, including the Caspen Bowden Awards in Privacy Enhancing Technologies, a number of awards from companies like Google and Facebook and others. And today he's going to tell us about his research in mobile app privacy when it comes to embedded AI, and very much looking forward to hearing more about his findings in this space. So Kassem, the floor is yours, and thank you for being here.
Thank you, Norman, and thank you all for attending. I think Norman just saved me the trouble of going through this. So everything Norman said is in this slide. So my research areas of interest roughly fall within users and security and privacy, but I take more of a user-centric view of security and privacy, especially look at how users interact with systems, what are the security and privacy issues that entail. So we look at the security and privacy of users interacting with machine learning systems, data and sensor privacy, online privacy, user authentication. I'll give you very quick examples of things we've done in the past. We looked at the security and privacy implications of users interacting with speaker identification systems. And here you can see my former PhD student installing a tube, and you can talk through a tube, your voice print changes, and you can use that to impersonate others. Of course, this is just a tube. It doesn't give you, it works pretty well in some cases, in lots of cases. Now we're 3D printing materials, so you can talk through them, and your voice print changes. But we're not going to talk about this today. Maybe next time. We have lots of works on data and sensor privacy. Basically, you interact with systems, what information is being collected about you, and how can we develop and design privacy-enhancing systems that can protect users. Today's talk will touch on this area of my research. A big chunk of my research is around online privacy, basically how to make privacy settings and privacy policies and notice and choice we're discussing earlier today more accessible to end users. I think CMU folks know these things very well. I'm not going to waste your time with talking about things that you know very well. And have done in the past research around user authentication that we're not going to be talking about. So today I'm going to be a bit in storytelling mode. It's not going to be like, oh, these are research questions, this is what we did. So I'm just going to tell the story of how our research unfolded for 2 years. Cool. Please interrupt and ask questions, because I don't want to hear myself talking for 50 minutes or so. Otherwise, it's going to be close to teaching, and I'm doing a teaching release this semester, so I don't want to teach. So the motivation of all of the things started with this billboard. This is in Vegas, in one of the CES, and Apple had this very nice billboard. What happens on your iPhone stays on your iPhone. This is like a very Vegas thing to say. And that got us thinking, like, what's going on here? And if you can see the URL over here is apple.com/privacy. So this is the new privacy argument. We don't need your data anymore. Everything you do stays on your device. Your privacy is protected. Yes?
Was that a response to the iCloud photo stealing scandal?
Might be, but Apple has, it's this and other things that happen, also interactions with law enforcement around like getting into phones. So Apple has been big on privacy, and it's very interesting when a company uses privacy as part of its PR. So that was very good. And that hinted towards a shift in computing paradigm. In the old days, like 10 years ago of mobile privacy research, this is how we envisioned the world. We have your apps running on a smartphone. They interact with a bunch of sensors, of course, mediated through permissions. You have user input. User data goes to the cloud, some stuff happened on the cloud, and then get some results back or some service back. This is what we did the research in like 10, 15 years ago. And the idea was what happens when your device leaves or might leave your device. And that motivated lots of research around information flow tracking, for example. Well, you have information sources, then the sink is the network, and you want to see if data here end up at the network. And we don't know what's happening actually on the cloud. Of course, there's lots of research that try to understand what might happen at the cloud. People look, say, at distribution of advertisements you see, distribution for personalized content that you see. People do data requests, these things that are enabled by CCPA and GDPR these days. You can look, if they do provide you with information about your profiles, you can try to guess what's going on. But then, computing paradigm shifted, and what happens on your device stays on your device. But data is still important, right? Like these companies make money out of data. So if the data is not leaving the device, it's staying on the device, these companies still need to make money, so something doesn't add up. Of course, the theory was, well, they don't need actually the data, but they can run some on-device processing, do whatever they want with the data, and then just the useful stuff can go to the cloud, and they can use it to do feed you services, feed you advertisements, and make money out of it. And of course, we can debate the privacy implications of this shift in the computing paradigm. One way to look at it, well, of course, it's better because your data is not leaving your device. That's good, right? You want your data to be on the device. But one can say, well, does it really matter that the data is not leaving the device if the end result is still the same? They're learning what they need to know about you, but your data is still on the device. And of course, it works well for the companies because companies don't want your raw data. Like storing your data means liability for them. Data can be hacked, can be stolen, you can have an insider threat, the government can come knocking and ask for this data. They don't want it. But still they want to make money out of it. So this is the win-win situation they got. Today, we're not gonna be discussing this privacy debate much. We're gonna look at a different angle. Because this shift in computing paradigm means that this processing might be happening locally. And for the processing to happen locally, that means that the algorithms have to be on the app now, which means we can actually take a glimpse of what algorithms are doing and what algorithms do they have inside the apps. So we started with this hypothesis. We can now know what happens to what happens on the device. Basically, what happens on the device, your data, and we want to know what happens with your data on the device. So that was the hypothesis back in September 2022. Motivated by this, what we thought was a shift in computing paradigm. Any questions? So we started this project or this research with great expectations. We had an ambitious objective. Well, apps have machine learning models in them. We're just gonna scrape like 1 million apps. We're gonna reverse engineer them, decompile them, find the hooks to the machine learning libraries, and then we're gonna write this big paper says, well, this is the distribution of data being analyzed, this is what they're collecting, this is what they're running, and this is what's happening. And we even had an idea of a pipeline. So this is a screenshot of one of the very early slides on this project, and it's just very easy. Well, we instrument Android to intercept machine learning calls from popular libraries. Some apps might have code obfuscation. Well, we're just gonna intercept GNI calls. I'll explain about this later. We're just gonna log all the inputs and outputs, and then scrape, download the apps, run them, and do collection, analyze the data later. And that's motivated partly by my view of how Android operated back in 2014, 2015, 2016, because Android used to be open source. Apps will use a library or will use an API. You can intercept that API, you can instrument the OS at that API, and then you can get whatever data you want. You can monitor the app's logs or the app interactions with the operating system. So we thought it would be easy. But then we had a question, like there's so many apps. Of course, and we're focusing on Android because we have lots of experience with Androids. We have lots of phones lying around. It is relatively open source. Relatively open source means the skeleton is open source, but still it's more open source than iOS. But still we had millions of apps on Google Play. And we were thinking, like, where do we start? Which apps do we start with? Because you have to start somewhere. We started with Google Apps, but that turned out to be difficult because it's very hard to draw a line between the operating system, the Android operating system, and the Google Apps. And Google Apps They have special privileges when they interact with system apps on Android. So we decided, let's put the Google apps on the side. Let's look at popular apps. What are the more popular apps on Google Play? Well, you have Instagram and TikTok. Billions of users. We thought, you know what? Let's look into these apps, uncover how they're interacting with machine learning, how they're employing machine learning. We'll learn about them, then we'll implement the scalable pipeline, and then we'll analyze the millions of apps. So that was the plan. And we even designed a very simple experiment. We said, well, we don't know what Instagram and TikTok are doing, so let's design a very simple app. We designed like a tutorial app that is using machine learning. We ran the app on an instrumented operating system. We're using Lineage OS. And we logged all the function calls. And we thought, oh, well, we can actually know how an app is using machine learning because they have to use these APIs. And we had an initial understanding. It turns out, like Android, they use TensorFlow Lite. So an app can either use a pre-made model, and then you can easily catch it by intercepting the classify native file, then classify native call. So if you intercept or you instrument that call in the OS, you know what the app is doing, you know what machine learning, what inputs are being fed and what outputs they're getting out of it. We also found that some apps don't have to use a pre-made model, a pre-packaged model in Android. They can develop their own model. And it's very easy. You train your model TensorFlow, you convert it to TensorFlow Lite, and then you use Android's TensorFlow Lite interpreter to load your model and access it at runtime. Of course, APIs are well defined in Android. We can intercept the calls and we can tell what's going on. And apps don't have to play with this or that. They can actually use their own custom model, own custom libraries, and do like the custom low-level API. And remember, we started our investigation with TikTok and Instagram. We looked at experiment apps, and then we found that it might be one of these two. Turns out that Instagram and TikTok were neither. They use their custom model, and they have their custom low-level API. Now, of course, 2 years later, that makes sense. Like, why would Meta use TensorFlow when they have PyTorch, right? But I don't know why we didn't think about this back 2 years ago. So we were like, well, we got stuck with Instagram and TikTok. And what we ended up doing, spending 15 months to try to understand what models are inside Instagram and TikTok. So the question is, can we find the models, the on-device models in these two apps? And that's the summary of 15 months investigation, and we published this paper in Oakland in 24. Any questions so far? So what we're gonna be doing today is just like how the research unfolded. And for the students in the room, it's important to see the things because you don't always start with research questions. You answer the research questions, you get the results, you write the paper. This is how you write the paper, but you don't start this way. You start with the hypothesis, something happened, and something happens, and something happens, then you get something interesting, then your advisor will tell you, well, this is how we pitch it. So this is a very non-linear story of how this research unfolded. And there are a couple of twists that are coming, so keep you hooked up. Before we get into the story of how the thing unfolds, we need to understand at a very, very, very high level how Android applications execute. Has anybody implemented Android apps before? Okay, I see. Nice. Well, when you write Android apps, you can write them two ways, actually three ways. You can write them in high-level programming language like Java and Kotlin, and sometimes you have native components of your apps, like things that you cannot run in Java, they're not too efficient, or you want to customize them some specific way. So your app has two components. It has a native component, and it has the Java or Kotlin-based component. And then these things get compiled. They get compiled to bytecode, and they then get compiled also to machine code. When the app is running, you take this machine code, you put it in Android runtime, and it runs on CPU, and then the apps run. So the main takeaway here is the following. Apps are implemented in two ways. They have native code components. They have Java components. And then but the actual app on your phone, you don't see the Java code. And you don't see the native code. You see the compiled version of the code. So it's bytecode in that particular case of Java, and then assembly over here. And it's heavily, heavily obfuscated because they don't want people to do what we're trying to do. So there are two challenges. The code is heavily obfuscated. So we need to overcome the obfuscation. And this is where we started by working on dynamic analysis using custom operating system. I'll talk a little bit about this. And then there are native libraries. And then the code jumps between native and Java, and you don't really know what's going on. So we needed to design a method by which we can actually track, identify if machine learning is being employed in an app, and then trying to identify what's happening, what are the inputs, what are the outputs, and reconstruct this machine learning pipeline. Of course, it would be a plus if we can track what's happening to these outputs. But we weren't able to do this. So this is like the twist that's gonna come later. Any questions so far? So the idea is we want to understand what so at this point, we have Instagram and TikTok. We want to know if they're using machine learning or not. And we're reverse engineering the apps. We're instrumenting the operating system and running the apps and see what happens. Of course, you need to run the apps. You need to expose all possible functionalities because you don't know which functionality actually invokes the machine learning code. So the first component, well, we started with this detection piece. Again, you have your app. Your apps are compiled. They are running on the operating system. What we did, we got Lineage OS, which is like an open source version of Android. Those who have done Android long ago might know Cyanogen mode. Cyanogen mode is no longer a thing, it's now Lineage OS. The idea is you can clone this Lineage OS, you can modify whatever you want, you can compile it, and it will run like a full-fledged Android operating system. So we instrumented Lineage OS, and particularly we instrumented the parts where function calls are happening. So we logged every function call that's happening with an app through Lineage OS. The idea here is the following. We wanted to see if an app is doing any machine learning components. So we logged all the function calls, we logged their arguments, their inputs and output arguments, and then we just did a keyword search. Is there anything that is reminiscent of ML? Is there like a tensor somewhere? Is there like a label or whatever? And there has been previous works, like 1 or 2 years before that, where they tried to extract ML models from apps, and they were doing keywords. Of course, they were doing them on popular libraries, which we're not doing. And we use their keywords, because you can come up with more elaborate list of keywords. So the idea is, run the app on an instrumented operating system, log all the function calls, log the input arguments, the output arguments, and do a keyword search and see if there's anything that is somehow related to machine learning. The next step was like, okay, once we know something is related to machine learning, we need to know what's going on around it. This is where runtime instrumentation using Frida happened. Does anybody have experience with Frida? So Frida is a very, do you know Ada Pro? So Frida is the open source or the free version of Ada Pro. Of course, we didn't pay for Ada, we paid for Frida. And the idea is you have something running, you can hook into objects, you can hook into classes, you can hook into memory locations, and then you can get the calling stacks, and then you can know what's happening at runtime. So from this thing, we know that there's some function related to machine learning. We hooked into these functions using Frida. Yes?
How do you still retain the symbols after it's been compiled? Wouldn't they throw away all the function names?
Great, we're gonna get to that. So this is what we see. So we're gonna go through this. Okay. So what we notice is when you compile the app, the same app version, the function names and the symbols are consistent. An app update, you have to repeat everything. So post-compilation, yes, everything changes. But at least different runs of the same compiled version, same symbols. It's not that simple. So you get that symbol, which is basically an obfuscated function name or obfuscated method. You hook to it through Frida, and then you get the stack. Who's calling it? What is it calling? Then we go through Ghidra for the native code, and we try to look through Ghidra and search for these functions that we have identified through Frida and see what's happening, what are their inputs, what are their outputs. And we do a JADAX decompilation of the Java files or the .dax files. And then we get the Java files and we do the same thing. Because Frida gives us symbols or method names, obfuscated method names, of things that are calling and being called by machine learning part. So we look for them in the source code. We don't have access to the source code, so we decompile source codes. We look at decompiled Java and decompiled C. Do you know Ghidra tool? So where did the Ghidra tool come from?
NSA.
It came from the NSA. Now, of course, the NSA now, they didn't mean for the tool to be open source, but then it became open source through one way or the other. Now they're proud of it and they maintain it. So we used Ghidra. Yeah, actually, we had a visitor from Cybercom, the US Army Cybercom, and they saw the student Jack working on Ghidra. They were very excited. But that's a different discussion for a different, okay? So we decompile the apps, we decompile the Java part, we decompile the native code part. We look at the functions inside the code, and then we try to build a pipeline. Of course, when we look at the code, we can find another points to hook into. So again, we go into Frida and hook into them. And doing this few iterations, we build the ML pipeline. We know, well, this is the actual machine learning method that's happening. These are the inputs, and these are the outputs. Of course, when we wrote the paper, we didn't make it look very manual. We needed to make sure that it is a framework. It is actually a framework, but there's manual labor involved in that framework. The steps are the same. You have to detect the keywords. So instrument the operating system, run the app, detect the keywords, hook into these functions, look through them in the native code and Java, find additional hook points, hook again, learn more, keep doing this till you reconstruct what's going on. So it requires, like, there's a method behind it, but it requires lots of manual work. Yes?
Question about the obfuscation.
Yeah.
Is the nature of the obfuscation such that each time you run it through, you get a different set of identifiers, or is it consistent from one to another, from one application to another, from one application to another?
So it is consistent from one compile to the other, meaning if you have a specific app version and you run it different times, they are consistent.
But if the app is modified,
And then everything falls apart, you have to repeat this.
and so they're not comparable across apps, certainly.
No. But but in different app versions, the behavior is a bit consistent. So whenever there's an app update, we can do this very fairly, very quickly. Unless there's a major change, and then you have to dig. But throughout the research, TikTok and Instagram have updated a few times, and we were able to get our bearings like where we were very quickly. I mean, the student, Jack, would come to my office and say, Kassem, they updated TikTok, this thing doesn't work anymore. And then he would spend 1 or 2 days and then get it working. So now he doesn't panic anymore. So this is putting it all together. Yes?
If I had to guess, most people, when they're writing machine learning code, they're probably using like standard APIs. So instead of just doing like some sort of keyword search, could you just have common libraries and detect it through there, or even check functions and see if they're making?
Yeah, so that's what we thought in September 2022. But turns out, because on TikTok, Instagram, they don't use this library, they use their own libraries. Like, for example, in the case of TikTok, they have this byte and N library. It's all written in native. It's very obfuscated.
Oh, they're using their own homegrown.
Of course.
I see.
And in Instagram, it belongs to Meta. Meta has PyTorch. Yeah, so
Okay.
it's
thank
very
you.
costly.
Yeah.
In your future slide, I'm just curious, the things that you highlighted that look like ML keywords are really like signatures, right? Like this is like a type that's being taken in, a vector of a certain size.
Yeah.
So is that what you mean when you say keywords, or did you?
Yes, that's how I say keywords.
Gotcha.
Yeah. So fingerprints.
Yeah.
Yeah. So like that, and any phenomenon that happens in the real world has to leave like fingerprints. It has to leave a trace. So we thought like they can obfuscate everything, but there are things that they're not gonna obfuscate, or they're not gonna go as far as obfuscate. Like, for example, a vector of numbers, a tensor labels. Once we found this key or this trace or this fingerprint, then we build our way out of it. So this is putting it all together. You have the app, you log all the function calls, all the arguments and the outputs. You find like what we call ML keywords, fingerprints, traces. And we call these as the evidence functions, and they're called something like this. So this is the obfuscated name. Then we go to Frida. We hook into this function, for example, over here. We get the calling trace. Then we have more functions. We go to native code, and we go to Java code, decompiled Java code, decompiled native code. We find additional functions. We hook into them and keep repeating this till we build the pipeline. Yes?
So like tensor, like the type is still,
Yeah, they still use the type tensor.
oh, okay, so because the type is not thrown away, you can use it?
Yeah,
Why is it not thrown away?
I don't know.
Oh, okay.
So we're able to reconstruct, and this is where things become more interesting. We're able to reconstruct parts of the TikTok machine learning pipeline. So it turns out when you're running TikTok and you open the camera from TikTok, like recording a video or something, and you want to post it. Now you don't post anything. You haven't posted anything. You haven't recorded anything. You just open the camera from TikTok. This library is engaged, libeffect.so, and you can understand why, because they might want to add effects to your faces or whatever. But you haven't done this yet. We just opened the camera. So the input image is captured. It goes to a pre-processing function. And then through this library, lib, byte, NN neural network, right? ML inference is being called on this image over here. And I'll show you later what is being extracted from an image. Outputs are saved to a register. Then there's another library that reads the output from this register. Now, of course, I'm having an arrow over here, right? This arrow is like 2 months of work. This is being saved in this register and who's reading from that register, because the data is like, there's not function calls and returns. There's lots of trampolines and complicated stuff going on here. Then there's a callback function executed on this register. And in the Java, this data is saved into an encrypted log file that I'm gonna show you in a few minutes. Now, what happens after this? We have no idea. We tried, we didn't know what happened. So this is like part of the TikTok pipeline. And you open the camera, machine learning is being engaged, and things are being inferred about your whatever. So keep that in mind. Instagram, the machine learning pipeline was simpler but more interesting in the sense they had 2 threads. Now you're trying to post a reel. You select an image or you open the camera, but you don't end up posting. You just by selecting an image, the thing runs. So they transform the photo into a bitmap. Then they create the machine learning thread, which runs the app through a model. And then 500 labels are extracted from the image. And then they select the top 10 scores. What happens to these 10 scores? We tried our best to dig through them. We don't know. And they also assigned it as a course project in my course last fall with the student. And the students dug a lot. And they were like, well, we don't know. Because remember, like when we started this project, well, machine learning is happening, all of these things are being extracted, and we were really praying that these summaries are going to the cloud. We couldn't find an evidence. So now we have a problem, like how do we write this? Because as you know, in the research and in lit, we don't like negative results, right? This is like, this is a sarcasm. Try publishing a negative result. What will the reviewers say? This paper has no contribution. Or I don't find the results surprising. It's like you're surprised watching a movie. Anyways. Cool. So these are the main results of the paper. For the Instagram case, you try to post a reel, the machine learning pipeline runs, and then 500 concepts are extracted from each image. So you have a concept, and interestingly, these concepts were written in English inside the app. We were able to extract them. So you have a concept, and each concept has a probability score next to it. And we were surprised, like, is this for real? Like, are they trying to mess with us or anything? Turns out no. So I asked the students at the time, well, let's make sure that this model is what it says it is. So we got these 500 labels. We saw which labels intersect with the labels in ImageNet. And then we throw those images at the model. And it turns out the labels are actually true. So the labels extracted by this model are consistent with the ground truth for ImageNet. Okay, so this is what it says it is weird. The other interesting thing, so that was the Instagram thing. And the TikTok thing, you open the camera to post a video. Even if you don't post it, by just opening, it runs face detection automatically. And then it tries to associate the face, predicts the age, and then predicts the gender or the sex of the face. And this is a demo of what happens. So what you're gonna see here is 2 things. You're gonna see basically the TikTok app. Jack has opened the TikTok app and he's just trying to record. He opened the camera. It doesn't record or anything. And this is the Frida output, like cleaned up a little bit. So you're gonna see like command line stuff. It was very ugly. Then Ashmit told Jack, clean it up a little bit. So this is the clean version. So this is Jack. Oh, sorry. So this is Jack, the start of everything happening here. So, okay, let me show you what's happening here. So Jack shows his face to the camera. The model automatically, face count, number of faces, bounding boxes of the faces, age, and the very interesting thing, boy probability. So boy probability is sex gender, whatever you want to call it. In TikTok world, it's called boy probability. And because Jack is Jack, the probability is 0.98. Age is mapped to 28 years old, and these are the faces. And believe me, we had lots of fun with this in the lab. Ashwin can attest to this. The interesting thing, okay, I'll talk about the other interesting. So, and Jack now puts his finger on the camera. There are no more faces. Okay. Then he shows his face again. Yeah, so when he put his finger, no more faces, and that's about it. Faces, no faces, faces, no faces. So this is when he put his finger on the camera, this is when he showed his face, and this is when the thing ended. So, but of course, we don't know what they are doing with these things that they're extracting.
It's interesting how much he's aged from the first time to this next time.
Yeah, so age differs, right? But same rough order of magnitude, 28, 32, if you're using this for age verification, it's probably okay. But we're gonna have more to say about age verification in a few minutes. Now Instagram, I told you there are 500 labels. Now I'll give you a scoop. There used to be 500 labels. The more recent version has 1,500 labels. So this is Jack again, showing his face to the camera. And these are some of the labels being extracted. Of course, there are 500 of them. But you can see, like, I think these are sorted by order, by probability. You can look at this classifier as a multi-label classifier. So one label probability is 0 to 1, second label probability is 0 to 1. So this is multi-label, and you're sorting labels by order, by the magnitude, by the value of the probability. So eyewear, face, obviously, beard, he was wearing a beard, sunglasses, I don't know. There's aesthetic strain rating, 0.45, and we had lots of fun with this in the lab. Like, what does aesthetic rating mean? And we'll all show our faces and see who's like more aesthetic. Until
I mean, isn't that what Mark Zuckerberg did first when he started Facebook?
I don't know, but
He was rating
this is
people on how good looking they were, right?
yeah. But I think this is not about how good people are looking. I think this has to do with the aesthetic of the photo itself with the scene. So it's not about the face. Yeah. And there are other things that are shown here. Of course, the list of 500 labels, I have it in a backup slide. It's very interesting, and I'll show you a glimpse about this.
Spaghetti.
Yeah. It gets weirder, I promise. But now going back to the story, how it's unfolding. So this was around, I would say, May 2023 or June 20. No, I think this was around September 2023. But we still have not found an evidence that these things or these labels are leaving the device. And I was like, what's the point here? Like, we can't just tell people we found these models. Like, if they're not leaving the device, what's the point? But then I was like, why do they have to hire engineers to train these models, implement them, develop them, put them in an app? I mean, what's the point? And then Jack had an interesting idea. Of course, this was the initial question that we had roughly, and this is where the pivot happened. Jack was like, you know what? We have access to these models. Let's audit them for fairness. Are there demographic disparities in the quality of the inferred insights? And that had to do with another research project happening in our lab where we were synthetically generating faces to test face recognition systems. And we had very fine control of the generated faces. I'll talk about that in a second. So Jack was like, can we use that data set to test these models and see what happens? I was like, Jack, you saved the paper. Or you saved the research. So of course, that was the pivot. Now, when we wrote the paper, did we say all of the story? Of course not. We started with these two research questions. Because of course, this is what we were thinking from the beginning. So this is, I know this is an untraditional way of presenting research, but it's very important to know that research unfolds this way. When you see like the final version and you see like, we had this research question, we did this. I don't know, that might happen. In this case, it didn't happen. So don't be discouraged if it doesn't happen then. Now, so we had a challenge. We have the models. Now we have to test them, and you have to test them on thousands of images. So how do we do that? So we have to inject the data sets to the model. For the case of TikTok, we were actually able to hook into the inputs and the outputs. So we were able to feed images to the Instagram app as if like we are feeding images to a model that we're running on some GPU. So we run the app, we have Jack had a Frida script, he gets the image, he feeds it into the model and gets the output. So he was running it almost locally. And if you're interested, we have the actual weights of this model, we have the architecture. So if we want to do any analysis on the model, like do membership inference attack, we want to do data extraction, whatever, we have the model weights here. And this would be one of the very first works that would look at an actual model in production. You're not looking at an API. We weren't able to do the same for TikTok because everything was buried very heavily in the native code. So what we ended up doing is the following. We did like a very sophisticated setup by which we have a phone and a screen. The screen will play faces, and then the TikTok is running, and then we're capturing the outputs from Frida. And of course, we would run the same phase like 5 times and get the outputs and make sure that they are consistent. Things that are not consistent, we throw them away. We tested TikTok with a fair face data set, basically a balanced data set of faces that are sampled from the Flickr data set, and they are manually annotated so that they have proper demographic balance and sex balance with the attributes. So you show face, and then you want to see, because they are properly labeled, you know the age and you know the sex of the face. And then we would see the outputs from TikTok and we want to correlate them to see if is the model doing correct prediction, and is it biased according to the demographic or something else. For the case of Instagram, yes?
Is there an assumption that that the individual images are independent of each other?
Yes, this is an assumption.
And did you check that assumption, for example, by showing the fair faces in different orders to see whether the same images were interpreted consistently when they were in different orders?
So that's a good question. I don't have the right answer. I'll have to ask how Jack ran the experiment.
I will leave it as an open question.
Yes. I would like to say we did this, but I'm not 100% sure we did this.
So I've had experience in an unrelated kind of application where the input order really did matter a lot.
Yeah. Now for the Instagram case, we had our data set of faces that are like that I'll explain in a second. And what we did is we took the faces and removed the backgrounds from the faces. So we just fed it a face like this. And we wanted to see like which concepts spike up according to what face they see. And that will allow you to see like spurious correlations. And you're gonna see what we observed. Very quickly, I mentioned here a custom data set. That was work happening in our lab at that time. We generated we designed a pipeline using diffusion models, blah, 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 blah. And then we get like a data set that looks something like this. So you have different demographics, and then you have different attributes, and then you generate faces of these different demographic and different attribute combinations. At the time, we had like a smaller number of attribute demographic combinations. Now we have a huge data set which has 6 demographics. Each demographic has male and female, and we have 20 different attributes, and we have fake identities, and we have multiple images of that identity for that bucket. So if you're interested in a data set to do any sort of testing, let us know. We have that, and it's open source. So we use this data set to test the Instagram model. So we started by testing, again, TikTok, and I don't remember in which order we show the images, but we observed something very interesting. Images of children get an age of 13, or like this is the median age for children as predicted by TikTok. And that's very interesting because we don't know why this age is being inferred or what is being used. But if, and there's a big if this model is used for any sort of age verification, children are being marked, the median is 13 years old, which happens to be the minimum age you can use this platform. As you get older, the age estimation becomes much more accurate. Of course, we conditioned all of these values on male, female. We conditioned all of these results on different demographic attributes like Asian, Middle Eastern, white, whatever. And in the paper, we have all of the statistical analysis and the null hypotheses and where does it fail and where is it more accurate. There are much more results in the paper around this. Then the Instagram experiment. We show faces without any background to the model, and we wanted to see which labels spike up. So when you show it, for example, like for an Asian man, whether there's an eyeglass or not, there's some correlation between eyeglass and Asian man. Asian woman, Great Wall of China. Why do you think that would happen? I'll give you a theory. These models are trained on what? On images from Instagram. Images of Instagram have selfies.
Tourist photos. Tourist photos.
Tourist photos, right? And then the model learns to correlate whenever it sees the Asian woman. There's probably Great Wall of China in the background.
So they're drinking on the Great Wall of China?
And I don't want to get into the weird stuff, but you say Indian man, beard, Indian woman, jewelry, white, like every possible stereotype that you would say shouldn't do, the model has learned. Of course, it has learned because we are, as humans, we're not like, anyways. Yeah, I hope this is what this is Instagram. Anyways, please don't be offended. This is like just results from a model that we did, and we have we have the faces, we have everything for rerun the experiments. Cool. So that was the conclusion of the first part of the investigation. So we're able to.
So that lets me re-ask the same question.
Here we ran.
If you're feeding it a lot of blonde white women, then I see blonde coming out as an attribute. If you're feeding it a lot of brunette white women, I would expect a different outcome, or I'd expect them to misclassify the brunette white women. Do you think this blonde attribute is coming from?
It might have been coming
the
from.
model or from the data set?
It's from the data set itself. For these things that have to do with the face, they might have been with the data set. But the other stuff over here, like Great Wall of China and the other things, of course not from the data set, because the data set had no background in it. And for example, beard, the data set that we generated had beard and had non-beard. So it had all the possible attributes. Cool. And then we had a question, like, what do the users think? Because people have been trying to get the perceptions of users regarding ML, or researchers have been trying to get the user perception regarding ML for a while now. And very useful, very important, very impactful research, but we don't think users have been put in a place where they see the actual model in the app that they use running on their data. So we want to get their raw feedback or raw responses when they see TikTok running on their face, and they are TikTok users. So this time, actually, we were guided by research questions and we followed the recipe. This time there were no twists, and the story really unfolded this way. So we wanted to measure, what do users think about AI and machine learning? When they see the real model running on their images or on their data, what do they think? What's their immediate reaction? And would their habits or would their perception change after they see this data? And here we measured it directly after exposed to these things. And then we followed up with the users 2 or 3 weeks later. We told them, hey, by the way, did you change your behavior after our study? And we got the data that we got in this experiment. The experiment was done an interactive in-person interview. We interviewed 21 participants. The interesting thing is we did a mass mail in the UW-Madison, and we got 800 volunteers. And we sampled 21 volunteers. So it was a very popular thing. I mean, we weren't paying people extraordinary amount of money, but the topic just like touched with people.
So were these students only, or?
No. So this is like the UW-Madison community, staff, faculty, and students. So I'll show the representation on the next slide. And the requirements to participate were the following. They must be a user of TikTok and Instagram. And now we say familiar because there was one particular participant who wasn't an actual user of Instagram. They were a user of Facebook, and their daughter had an Instagram account, but somehow slipped through the user study. So we can no longer say must be a user of Instagram and TikTok. So we added that condition just to soften the language a little bit. Of course, it has to be in person, so they came to the lab. Actually, they came to my office. I was traveling, so all the experiments were run in my office, and they must be 18 years old. So these are the experiments. These are some participant statistics. We had, I would say, a good age distribution regarding like you're doing this in a university setting. So we didn't end up with a bunch of 18 to 25-year-old people. So that's important. We also had better than I expected in terms of gender representation. Of course, we would like to have this more balanced, but it was not. And then we performed like a semi-structured interview. It was like the interview had 3 phases or 3 stages. The first stage, you come in at all within the same setting, but the first part of the interview was like we chat. What do you think? What is your initial perception, understanding about machine learning AI? Of course, we don't ask them the question this way. We probe them around this, but this is the general theme of the probing. We try to understand like how frequently do they use the app, and when do they use the app, and then we ask them, what do you think? What is AI and machine learning? We try to get their understanding of the actual technology because that's important. But then if we wanted to show them things about how machine learning is running on TikTok and Instagram, we were like, we need to teach them a little bit about machine learning. And we used this thing, which is teachable machine learning from Google. Has anybody seen this before? This is a great tool if you want to teach someone machine learning very quickly. So the tool goes as follows. You open a browser tab, and then it tells you, you want to train a model, choose a label. Then you choose a label, you choose a set of labels. They're like, okay, great. Give me examples of these labels. You can open your webcam and you want to say like eyeglasses versus no eyeglasses. So you just put like this and do things like this and then record images. And then great, eyeglasses. You put your eyeglasses on, you look at the thing, webcam, we have images of people eyeglasses. In this case, it's like sleepy left and sleepy right. You click train, you have a model. And then they will tell you, well, let's try out the model. Open the webcam and then you try different combinations, things like this. And the interesting thing is you can see the scores changing over here. So you get a feel that there is a concept of data, there's a concept of a model, and there are a concept of scores over here. We wanted people to learn what these scores, what is the concept of a score. Like, I understand, like in 10 minutes you can't teach people machine learning, obviously, but at least get a feeling of this. And then we demonstrated the apps. We had the phone hooked up with TikTok and Instagram, and we would ask the users to actually run the app and look at and put their faces in front of it, put objects, and then look at the labels. For the TikTok labels, it was very easy. You had like 3 or 4 things you want to see. There's a number of faces, age, boy probability, and age. For Instagram, you had 500 labels. You cannot really visualize 500 labels easily. So we had this very sophisticated bubble thing where you have a hierarchy of the labels. They can zoom in, and then they can zoom in and see labels and things like this, just to get a feel of what the app is predicting about them. Then we measured their behavior changes. What do you think? Would you change your mind? Would you change the? Would you use the app differently? Would you do this? Would you do that? And then we thought, you know what? 3 weeks later, let's ask them again. Did anything longer term happen? Interestingly, out of the 21 people, 17 people responded to our survey, which is, they didn't have to, but they did. Following proper procedures and qualitative research, we did what we needed to do in terms of coding, thematic analysis, and we got some emergent themes in the research. And I'm gonna go over our findings here fairly quickly. People were like 15 people out of the 20 associated AI and machine learning with advertisement. And this was before they saw anything about TikTok and Instagram. This is just the raw inputs. And these are some of the quotes. This is from participant P15. Of course, the avatar here doesn't mean anything regarding whether it's male, female, whatever. So this is just a random thing. So don't look too much into what the avatar is saying. But these numbers do mean anything. If you see P15 on a later slide, it's the same P15. Some people thought, well, it is for functionality. Like in the labels for Instagram, there was a nudity label by the way. And there was a violence label by the way. But people were associating these things before they actually saw the outputs of the model. When they saw the actual model implementations, so people had different reactions. In the case of TikTok, people thought it was invasive. In the case of Instagram, they thought it gives users agency because the model runs when you're trying to do selection. Now, is there some sort of anti-TikTok bias happening here? Quite possibly, okay? Because this is done at the University of Wisconsin-Madison in the summer. So although I showed you the age, I showed you the gender distribution, but I didn't show you the ethnicity distribution. Because who still lives in Madison in the summer? Anyways. And then people have different opinions. Some people still thought like TikTok still collected less data and might be harmless. People saying, well, Instagram is trying to understand more about this picture, but they don't have an explanation for the why. And this goes into now that, so now we're like looking at a new realm of this kind of research. This is not much about privacy per se. There's another thing about transparency. So you have an app that's deploying a model, and the model is doing all of these inferences, but you don't know about it. Should the users know about it? And if the users should know about it, what should you tell them? So that's still an open question. And some users thought, well, we would like to see what's going on, at least why this is happening. During the interview, we asked people, would you change your mind? I think people said, well, some people said we won't change our minds at all. I'll just keep using Instagram. Some people said, well, I might change my opinion. For example, like posting pictures, starting a record, or opening a camera. I will be even more conscious well before opening the app. So these are the immediate reactions that we got about behavior changes. Then we got the results of the survey that we ran or conducted 2 weeks later. So this is like P4. So P4 said, feels like I've already been compromised per se. I don't know if it makes too much of a difference if I stop now using the app. 2 weeks later, well, I reduced the permissions for these apps to access personal data. One other respondent say, now I don't point to the camera when using the app at the random things. I'm very careful about where I point the camera. So, which is like, I wouldn't say is an evidence, but it's a data point saying that if you make these practices transparent to users, they might behave differently. And we might need to tell users about this. So in summary for this part, users had different opinions about what is the purpose of AI and machine learning in apps. Some thought it was for advertisements, some thought it was for functionality. The difference between whether Instagram is better or TikTok is better, what positive sentiment they had about the app, really had to do with their internal biases, obviously. The implementation, like what is actually happening. Is it triggered when you open the camera, or is it triggered when you try to actually do something? This triggering mechanism actually affected how people perceive what sentiment people have about these models. And of course, what the outputs of the models are. And when people like interacted with the models, people like the majority were fine with the models, they're okay. But then we observed that I think 4 out of the 17 reported that they have changed their behaviors after the things. So this is like the story of research over 2 years when we like started with this, what happens on your device stays on your device all the way to users' perceptions. So what happens next? Well, because now we can dig into apps, we can look into personalization algorithms, because this is not, the vision model is not the only model that's running in an app. For example, you see a TikTok here. Why are you seeing this TikTok? How was it selected? And what does TikTok look when it's the app? What kind of features does it look for when it's making the selection? Are you curious? So these are the features that go into the recommendation models. And this is from the reverse engineered apps. I didn't know how to present it. These are the features. So if you wanna dig through the features with me, you're more than welcome.
But is there any overlap between those labels and the ones you picked in the pictures?
No, this is a TikTok. So this is just the recommendation model, which is looking at how you use that. It seems to me they record the last 10 videos you interacted with, and they measure like the play time for each of these videos. And then, of course, they keep track of the average time played, the time play max, and the minimum, and the minimum, and the total. This is like a benchmark. The number of comments, how many times you skip. Do you skip a video? Do you comment on a video? The duration of interaction with, the duration you stayed on a video even if you didn't play it, that is a feature. Did you like the videos and all of these things? So this is to say, when you're using an app like TikTok, everything you do, every touch you do is a feature. And those are used to select the next thing you want to see. Why? Because they want you to be hooked to the app. So they want to feed you things that are you're more likely to deal with. We haven't done much with this data yet. This is like 2 weeks ago we got this model. We don't know what to do with it just yet. But we know these things now. Another thing that we're thinking about that we haven't decided what to do. Now we have access to the models and you have an interface to the model. What if we let the users control what outputs should be? Like they can, for example, reduce the beard score, or they can increase this kind of score, or reduce the violence level, or whatever. We have this kind of control now. If you can hack your way around it and change what the app knows or thinks about you. But of course, is this a good idea? And this is the only AI-generated illustration in the whole paper and the whole presentation. So I was like, well, I need to put something. I didn't want to be a dry slide. So, and this is a ChatGPT generated. Works it's actually very. I was impressed. So if you have this direct access, should we let the users change the model outputs? I don't know. This is an open question because I can see the pros and cons, right? Giving users control and agency, that's one part of it. But then if this is being used for some sort of client-side scanning to avoid violence or whatever, then do you want users to be able to reduce the violence score on the video they're posting? And this is, again, this is a traditional security thing. If you're doing any client-side verification, the adversary can overcome it. So it also appears here in this setting. Another set of open questions, we don't know what to do with this. But these are ideas that we're thinking about, following up on the things that I discussed. Of course, this work took lots of student effort to get into this, but the master, most of the work was done by Jack, who saw his faces a couple of times. And we had Bengasu, Jingjae, and Shirley assist in the user study. Leah, Shaimam, and I'm zoning on the name now. And Maggie, Shaima, and Leah, undergraduate student. They helped with the TikTok and Instagram analysis, and Suman, professor in CS, was our collaborator on this project. Thank you.
So probably there are a bunch of questions.
So these are the 500 labels.
3 of you mirror.
They are in the paper also, so it's like I'm not showing you anything. But if you want, we have the 1,500 labels, the new ones.
So please raise your hand if you have a question. Yeah, go ahead.
Yeah, so thanks for this very impressive research. I was wondering, so back to your opening question, do you find any evidence that any of these kind of analysis from ML is kind of sent to the Instagram model?
No, we don't have any evidence.
So it's still locally, but this by knowing this, your photo is being processed will affect users' behavior.
Yeah. So this is actually a very interesting thing, and that might change, at least from my perspective, when I did my initial research in my PhD around privacy, I always had this thing in my mind. There's the trust boundary is, this is the phone, there's the trust boundary, and this is the cloud. What happens here, I trust it. But maybe we should revise our trust boundary. There's me, and then there's the app. Once things go to the app, I have no control, whether the app is local or remote, because the local app is now an extension of the cloud. And the companies do benefit by pushing processing to your device. Why? They reduce the reliability, and you pay for their compute. Yeah?
So you mentioned that they label pictures and images that whatever the camera sees.
Yeah.
And there was a slide where you mentioned that the TikTok also uses the previous videos that you have seen or the videos you have seen.
So this is different. This is the recommendation personalization model. So this is not the vision model.
So, okay, so the vision model that does everything locally, and what happens after that?
We don't know. So this is where it gets a bit disappointing, I know. I keep building, and then I tell you, well, it saves to an encrypted log file, and then nothing. We don't know what happens.
You can also like hook into the Frida module.
We tried. I mean Jack.
And that would be interesting to see.
Yeah.
But is that file being sent back to the server?
No, we don't know. We haven't found evidence. Is it proper like lawyer speak? So,
No evidence for it.
yeah. So we did not find evidence for this.
And what about the other model that you showed where it took input?
Here, the instant.
Not this one. The one
The other one. Well,
ML config one where it takes input from the last videos you have seen.
this we just looked into this. This is like 2 weeks old. We don't know. But this I envision like this is it's very conceivable that the next video is chosen based on this. So idea is probably this goes into a model that spits out like distribution of IDs of videos that you need to show the user. It samples from distribution shows you.
But there's no evidence of like the user labels and these interacting with
No. But this is recorded.
So one idea might be to ask these companies, right? And
Yeah.
obviously you could ask directly, I mean, as a faculty who's done research on this.
Yeah.
Another option might be to talk to a regulator who could potentially ask also, and maybe they
Yeah.
be more likely to disclose. So have you,
So we tried to do the outreach. So we published this thing, obviously. I think we reported findings to Facebook. I don't remember, or to Meta. Actually, I shouldn't say that. I don't remember what we reported and what we didn't report. But we tried to publicize this as much as possible. Hopefully, somebody catching attention and looking into this. Didn't.
I mean, you can also talk to journalists, obviously, and then they might call
Yeah.
the company and
I
say,
mean, yeah, we can. I mean, we tried. Not very successful.
So these were all the apps that were based out of US. Like
2 apps, yeah.
But like, is it the same version that is deployed in Europe and they have the same
Possibly not. We don't know. We didn't try this in Europe. This was in Madison, Wisconsin.
Because I was thinking
Yeah. It might be. These apps are downloaded in Madison, Wisconsin. That is a much idea. Yes.
So I apologize, you may have covered this, but I was teaching till 12:30.
That's
How did you infer the model? Because
Oh,
you did
that's like
some-
yeah.
that was
So
the first half of it. I'm going to meet you, so I'm happy to chat. But
that's
some of us may be wondering, right? Like,
So this is how we were able to get it. So basically, it's a combination of static and dynamic analysis. You instrument the operating system, you run the model, then you find any trace of machine learning happening. And those traces are basically functions that are obfuscated. You hook into these functions in Frida. Then you get these functions, then you decompile the app, the native code and the Java code. You look at the stack trace from Frida, you look for these things, and then you try to identify more targets. You hook into them, and then you keep doing this until you build the pipeline. Lots of manual labor here, but there's some method.
so this sounds fascinating. Could you do that for any app, or how much effort is it to do it for this app versus?
Very good
any-
question. Once the student has took us 15 months to get here. Now Jack can do it for any app.
He can.
He can, because he has been doing this for a while. Like the effort for a new person to do it, not much, I would say. If they are patient into reverse engineering.
And this works for on-device ML. 'Cause
Yes,
if-
yeah.
If you're sending the data back,
Well,
you can't do anything.
You can't do anything.
I see. Okay, great. Thank you.
so what does,
So how did you know what the keywords were?
Oh, there's a prior work where they're trying to extract ML models, and they just found traces of words like tensor, array, whatever. So we got the keywords from those papers.
No, but you have keywords for concepts.
Yeah.
How did you get those?
Oh, the keywords of concepts.
Yeah.
Oh, yeah, that's actually a very good question. You're talking about these concepts over here. So
Yeah,
once we
they-
reconstructed
It's an amazing collection of things.
yeah, so once we reconstructed the pipeline, there was a JSON structure inside the code that happens.
So those words were in that adjacent.
These words were in the app, yes. We did not invent these words in the app. We were as surprised as you are when we found them. Which led us to running this experiment. Get like images from ImageNet and see if the score is high or low. And turns out it's high. Yeah.
You showed earlier, can you go back to that slide where I think Jack was like,
This one?
well, that too, but there was
Video.
one before that where you maybe,
The video?
yeah,
Yeah. So
just
this
so
is
that you can see. Yes.
So this is student Jack. Sorry. So show the face and see what's happening. So this is Jack's face. And these are the labels.
Yep.
And then there's the TikTok case, where whenever you open the camera, it extracts all the faces in the frame. Number of faces, coordinates of the face, estimated age, and boy probability.
Which we already had a good giggle over, I think. Just the name of that.
I know this is recorded on. I'm not gonna make the joke I was about to make.
I think you just did. But so, what does the privacy policy say, if anything? Does it reveal anything?
It is vague.
At any level?
Yeah, we did some analysis of privacy policy. Like these behaviors are covered by the privacy policy in a vague way. Yes.
It is covered?
Yeah.
Okay. Do you remember what they say?
We can dig up the paper very quickly because we have the thing in the paper. Let's try it. And yeah.
I mean, the fact that it says something indicates that, presumably if they were doing something particularly egregious, they would have to probably disclose it at some level.
Okay, getting there. So this is the part of the paper that we talk about laws.
Okay. Can you blow that up a little bit?
Yeah, that's what I'm trying to do, but my fingers, I think we're just somewhere over here.
Maybe I can do that. Actually, I can do that. Privacy policy, I can read it. Okay, so TikTok, Instagram states, okay. They may use the camera feature for various purposes, I see.
Yeah.
Forming analytics, personalizing recommendations to advertisers and partners.
Basically, whatever they want to do with it.
Okay, so then they could really,
They are covered, yeah.
right.
I mean, I agree with you that there are still a lot of important questions, even if this stays completely global.
Yeah.
But if you ever do get an inkling of sort of how to trace whether or not some of this goes back to the cloud, I think that would also be like
I know.
very interesting.
No, this is what I said, gets a bit disappointing.
Yeah, so that clearly indicates that, and obviously this is written by TikTok, but they're running it on iPhones. And so that statement in Las Vegas clearly is pretty misleading.
Yeah, for those who weren't here for the first part. So this is how it all started, like the presentation and the research. It started here.
Not true.
But this is the OS, this is Apple.
Yeah, I mean, I know, I'm not talking anything about Apple.
Yeah.
I'm just talking about the privacy claim that this thing is synonymous with privacy. That's the point I'm trying to make here.
So did you try to see if these apps have like do socket calls out to send these data items?
Oh, we tried very hard. We couldn't find any evidence.
That they do or do, you couldn't say anything whether
Can't
they
say
do or do
anything
not.
because we tried to. So there are multiple ways you can do into this. Network communication is complicated in these apps. So you have two ways. You either have to hook into the network methods and see what data is going out, or you have to intercept network traffic.
Yeah.
Intercepting network traffic is hard because these are encrypted. And they tell me, well, you can do man in the middle and revert and take out TLS, but the certificates are pinned. So they do certificate pinning. So you cannot really run man in the middle. So we weren't able to get much in terms of network traffic.
Even with certificate pinning, you can, yeah, I get it. But we should check, when we check more.
Thank you.
Well, they're certainly disclosing, I'm looking at TikTok here on the App Store. I mean, they're certainly disclosing all sorts of things in their privacy labels.
Cool, thank you.
This was great, thank you.
Thank you very much, Kassem.
Yeah.